right, so I'm just going to go over the answers on our practice test here. I thought it would be helpful. So we're asked to determine an exponential function. It looks like this. X is in the exponent. And we're asked to figure out what a and b are given that the points 0, 5, and 1, 10 lie on this function here. So what we do is we replace, this is my x coordinate, this is my y, so I take what x is and I throw that in, and what y is and I put that in there as well. I'm trying to figure out what a and b are. So when I plug in 0 for x, I get a times b to the power of 0, because I'm plugging that in for x, equals 5. Well, b to the power of 0 is 1, so we get 5 equals a times 1. So therefore, a is just 5. Which means that I'm going to go up here and I'm just going to get rid of my a and make that value be 5. I use that 0.05, which makes it useless now. So now I'm going to look at my 0.1, 10 over here in hopes to figure out what b is. So I'm going to substitute again. I'm going to replace x with 1, 10 with y. So I get 10 equals 5, b to the power of 1. Well, b to the power of 1 is just b, so I get 5b is 10. Divide both sides by 5. Clearly, b is 2. So this means my exponential function is y equals 5, b is 2. So I'm going to replace b with 2. So I'm going to write 2 here. And I'm going to denote it like that. Geez. Make that just be an x. There we go. Okay. So that's my exponential function. There. All right. I'm going to go on to number 2. We're asked to determine an exponential function again. Looks like that. It contains the points 0, 10, and -1, 5. If you're noticing a relationship develop, when I plug in 0 here, this value becomes b to the power of 0. So a always must be what y is. Whenever that always happens there. So this value for a is going to be 10. But I'm just going to do it out anyways. You might be jumping to there. So y is 10. X is 0. B to the power of 0 is just 1. So we get rid of this. 1 times anything is, so we realize a is 10. I'm going to go back up here. I'm going to erase a. I'm going to make that value be 10. We got to figure out what b is. 0, 10, this point, we've used it. It's useless now. We got to look at -1, 5. When I plug in -1 for x, I get 10 times b to the -1. It should spit out what? 5 right there. Now I'm going to divide both sides by 10. I get 5 over 10 equals b to the power of -1. In other words, 5 over 10 is the same thing as saying 1 over 2 equals b to the power of -1 is defined to be 1 over b to the power of 1. This value right here is right there. And, well, this means that b is just 2. They have the same numerator. B is going to be 2. So I look at my function up here, I replace b with 2. And that's my exponential function there. 10 times 2 to the power of x. Let's go over 3. Another exponential function, y equals ab to the x, points 0, -20, and 0.5, 10. I do the same thing that I've always been doing. I plug in 0 for x. I realize this value is 1, so y equals a. So this value right here is negative 20. That's negative 20. So I'm just going to write y equals negative 20 b to the x. I'm jumping here. X is 0.5. So I'm going to replace x with 0.5. And it should spit out 10. So I'm going to write 10 over here. I'm going to divide both sides by negative 20. So this means that we can kind of ignore the zeros. So we get negative 1 over 2 equals b to the 0.5 power. Now when I look at this, I'm really looking up here and I say, well, this is the same thing as saying b to the 1/2 power. So it's the square root. So what I'm going to do is I'm going to square both sides. And when I do that, when I square 0.5 right here, when I'm squaring this whole entire thing right here, I'm going 2 times 0.5, which is 1. So this implies that we get b to the power of 1 on that right-hand side of my equation. And when I square negative 1/2, I go negative 1/2 times negative 1/2 is a positive 1 over 4. So in other words, b is just 1 over 4. So I'm going to replace what b is right here. I'm going to throw that up top as well. So I have b is 1 over 4. I'm going to be careful here, so I'm going to include parentheses around the whole thing. So b is 1 over 4, and a is negative 20. So I'm just going to go up top. A is negative 20. So that's what that exponential function is. You could also just write it as negative 20 times 0.25 to the power of x. I can write. So that's 3. Page over. Four contains the points 0, 3, 3, 81. Y equals AB to the x. When I plug in 0, it should spit out 3. So I'm going to plug in 0, should spit out 3. B to the power of 0 is 1. So I get 3 equals A. So I'm going to look up here and replace A with 3. Now I got to figure out what B is. Well, we're given the point 381 is on here as well. So I'm going to replace x with 3. And then 81 is what y is. So I'm going to replace 81 there. Well, that's nice. I have to divide both sides by 3. So when I do that, 81 is divisible by 3. So I'm going to go 81 divided by 3. If I put a 3 here, it's not 3. It's too big because 3 times 3 is 9. 9 is bigger than 8. So I'm going to put a 2. So get 2, 6. 8 minus 6 is 2. 20. Bring down the 1. And then 3 times 7 is 21. So I go a 7 here. So I have 7 times 3 is 21. I subtract that off, 0. So I get 27 over here. 27 equals b to the power of 3. Now I'm trying to determine what b is. It's a power of 3, so I go, well, it seems like it's a power of 3, so I go 3 times 3 is 9 times 3 is 27. So it's 3 to the power of 3. So this means that b equals 3. If you want to do it a little fancy way, if you have a really big power, you could just take 1/3 power on both sides. You could do that as well. Or in radical notation, you could do raise it to the third, like that too as well. But that's how you do that one. Oh, so yeah, b ended up being 3. So right here, b should be 3. So that's your answer right there, because that's what it's looking for. So b is 3 right there. So you do 4. 5, it says simplify this thing. Well, you're just going to multiply these values here and here. You're going to keep the square root around them. You can do that. So you get 2 times 18 is 36. Well, that's nice. The square root of 36 is 6. So we get 3 to the power of 6. We have to do this out. So 3 times 3 is 9 times 3 is 27. 27 times 3 is 3 to the power of 4. So I'm going to write 27 times 3 is 3 to the power of 4. So that is, you get 21 here, 6, 7, 8, 81. 3 to the power of 4 is 81. 3 to the power of 5. Well, so I could go times 3 times 3 would be 3 to the power of 6. So in other words, I'm going to go 3 to the power of 4, which we said is 81, times 9. So I'm going to go 81 times 9. 9, 72. So I should get 729. $729 is that answer. When I simplify that one. All right, I'm going to go to 6. It says simplify this thing. Well, this is really square root 25 times 2. Square root of 25 is 5 times the square root of 2. And that's simplified. So that's how you do 6. Seven. We're asked to simplify 3 to the power of this thing divided by, 9 to the square power of square root 2. So first off, I got to find the same base. So 9 is really 3 squared. So I'm going to write 3 squared like this. Gosh, if I can write. And this is kind of ugly looking. I hate that division symbol. So I'm just going to rewrite this as 3 to the power of 5 square roots of 2 divided by 3 to the 2 square roots of 2. So just so I can look at it a little more. So this thing here is the same thing as this. So I'm going to erase this. Well, they have the same base, and I'm dividing, which means I can take the value here and rewrite this as 3 to the 5 square roots of 2 power minus 2 square roots of 2. You treat this kind of like a variable here. So you go 5 minus 2 is 3. So we get 3 to the 3 square roots of 2. 3 to the power of 3 is 27. If you want to do it out, you start with 3. 9 times 3 again is 27. 3 to the power of 3 is 27. So I get 27 right here, square roots of 2. And that is my final answer for that one. That one was fun. That's 7. Eight says, what is the range of the function? To determine the range of the function, f of x equals 5 to the power of x plus 10. If I plug in a value like negative 1,000 here, I raise 5 to the negative 1,000 power. That means 1 over 5 to the power of 1,000, which makes this value right here essentially 0. If you plug in, you have a value of a number and you raise this to a super large negative number, as this goes to negative infinity, technically, this value becomes 0, so you're just left with 10. So what happens is that, and you can think of this as just 5 to the power of x right here, if you're looking at this here. So it actually, it dies off, this value becomes 0, and it kind of hits 10. So it goes 5 to the power of x is, here's 10, and it looks like this. So it has this horizontal asymptote right here at 10. And you can also think of it as a parent function where, 5 to the power of x looks like this. 5 to the power of x where it hits right here at 0, 1. 5 to the power of x as x gets really small, it becomes closer and closer to 0. And then you just take this function and you shift it up 10, because you're going to move it up 10 here. But you can think of it either way. As x becomes a super large negative number, this value goes to 0. So it just barely, it's a little bit above 10, so it just hits it right there. So my range here is from 10. It doesn't include 10. So this means it includes 10. So it goes from 10, so it's open at 10 through, and then it goes from 10 all the way up to infinity. That's my range for that one. The domain here is what x can be. So here, range was what all the values that y could be. Y could be a value a little bit above 10 all the way up to, but not quite, including infinity. That's my range. My domain, x can be anything it wants. It's not like x is separated here. X can be anything it wants, so the domain is the set of all real numbers. You could also denote this as negative infinity to infinity if you want it to be fancy. Now we're asked to complete the table below using decimals. So we have x, f of x, negative 2, negative 1, 0, 1, 2. When we plug in negative 2 into my function, when I plug in negative 2 here, I get that you get 5 to the negative second power. So I get 5 to the negative second power plus 10, which is equal to 5 to the negative second power is 1 over 5 squared plus 10. 1 over 5 squared is, well, that's 25 right here. So I get 25. I don't have a calculator, so I'm going to rewrite this again. If I multiply this by 4, I have to multiply this by 4. So I get 4 over 100 plus 10. This means I move the decimal over 2 to the left. So I start here, 1, 2. So I get 0.04. So it's equal to 0.04 plus 10. In other words, it's 10.04. So I'm going to erase all this. Here, 10.04 is the value, which it spits out here. which kind of makes sense because as x becomes more and more negative, and you can already see it, it's becoming closer and closer to 10, but it never quite hits it. It's actually really steep. Okay, at any rate. When x is -1 here, you get 5 to the power of -1 plus 10. 5 to the power of -1 is 1 over 5. I want to rewrite this as a decimal. 1 over 5 is the same thing as saying 2 over 10. So it's really, if I multiply this by 2, I multiply that by 2. So I get 2 over 10 plus 10, which is 0.2 plus 10, which is equal to 10.2. So I get 10.2 here. When I plug in 0 for x, I get 5 to the power of 0 plus 10. 5 to the power of 0 is 1. So I get 1 plus 10, which is 11. That's 11 right here. Here, 5 to the power of 1 is 5. 5 plus 10 is 15. 5 to the power of 2 is 25. 25 plus 10 is 35. So there's my table there. Number 9 says, is this growing or decaying? Is this getting bigger? Is it growing or is it decaying? Is it dying off? So, well, here, this value is positive, so you know it's going to look like, just kind of think of 3 to the power of x. As x becomes huge, this value just goes way off to infinity. So it just goes, as x becomes huge, it goes way off. As x becomes more and more negative, this value becomes closer to 0. This just makes it times 5, so it doesn't really flip it or anything, so it just kind of dies off here. So we see this function right here. It's growing. It's growing. It's growing. All right. It's getting bigger. I'll get rid of that. Number 10 states y equals 100 times 0.7 to the power of x. Here, in general, if b is a value, let's say between 0 and 1, what's happening is that when you're getting 0.7, you're taking 100 times 0.7, 70% of it, this value, you raise it, you keep taking 70%, 70%, 70% of 100, it goes to 0. So this function, it starts out and it just goes, it gets closer and closer to 0, so it's decaying. This one's decaying. When we plug in 0, it should spit out 100, but that's not the point for that one. So that one's decaying. So that's 10. 11, an investment of $25K, so you get $25,000, is said to grow over time with a 15% annual interest rate. So it's growing, which makes 15% be the same thing as going, after the first year, you're gonna go 1.15. That's how much money you're gonna have. It's not like the value is getting smaller. This value would take 25,000 and multiply it by 0.15. It would make it get smaller. So we're actually wanting to have we're gonna put a 1 here. So we're gonna multiply that by 25,000. So it's getting bigger here. for the first year. Given t is the number of years, what is the correct balance over time? So every year, so after the first year, you multiply it by 1.15. You do it again after the second year, it's times 1.15 again. So this means our function is really, it looks like this, 25,000 times 1.15t, where t is the number of years. So this would be our equation for that one. So that answer would be B there. 12 says, what is the range? Determine the range of y equals 0, y equals 7 times 0.8 to the power of x. As x becomes huge, and don't throw in a value like 100.15. Throw in a value like 100. Like think of it as an integer. It's easier to think of these things as integers. When you take 80% of 7 100 times, you're going 80% of 7, 80% of that, 80% of that. The value is becoming closer and closer to 0. So what happens is that this thing goes, and it goes closer and closer to 0, but it never quite hits it. So it just kind of goes like that. So you have this horizontal asymptote right there. It never hits 0, which means that we're asked to determine the range here. So our range, it never quite hits 0, so it's open at 0. And then it goes, our set of y values, our range, goes from 0 all the way up through infinity. So that one would be A. Our range would be that, range. Range is a set, it's that. 13. Last one. It says, what is the range of y equals negative ab to the power of x plus c, where a is a value greater than 0 and b is a value between 0 and 1. I wanted it to be harder than this. I made it a little easier. The whole goal is to kind of, you want to think of values right here as like, you're almost like you're substituting in. So like a is a value greater than 0. So I mean, we have all these variables here, which is great, but I want to see what this thing kind of looks like. So a is a value greater than 0. I'm going to replace a with an easy integer like 5. So y equals minus 5. So I'm going to write a little note to myself. A is 5 here. So a is a value greater than 0, so you got that. B is a value between 0 and 1. I'm going to choose, 0.5, because I like 50%. So B is a value there, so to the power of x. A is 5, B is 0.5. And C, I don't know what C is. I'm just going to make it up. I'm going to say C is equal to 3. So I can kind of look at this, what's going on here, and think of my range in terms of A, B, and C. So if I was going to graph this thing here, this negative 5 says I'm going to take my exponential function here, and I'm just going to take it and I'm going to flip it. So it's in the negative vicinity here. So I know it's going to look like this, or it's going to look something like that. It's taking it and it's flipping it. And as x becomes super large here, like let's consider what happens when x becomes way huge out here. What does this function kind of do? Well, x becomes, consider this to the power of 1,000. You're going to make this be 1,000. So negative 5 times 0.5 to the 1,000th power. This value is going to be essentially 0 here. So this value is going to be a small little negative number plus 3. So it's going to be a value. So this thing is dying out at 3. So this exponential function looks something like this. So the horizontal asymptote right here is right at 3. It never quite hits 3. And you can verify it by throwing in a number like x. When x is, I don't know, 1,000, I encourage you to take it and plug it in and realize that this value right here is going to be, why did I make 3 be over here? That value is -3. 3 should be up a little higher. I don't know why I put 3 there. It hits 3 right there. All right, so the range would be from -infinity all the way through 3, and it would be open there. Now I realize that C, we called C 3, so I'm going to just replace this with C. So that's my range. And that is how you do it.